So I guess we can start. Vanira, can you please confirm whether I'm audible or not? Thank you, Vanira. So, good evening all. My name is Itura Singh Sujawat. I'm Prime Minister Research Fellow in Department of Earthquake Engineering from IIT Roorkee. I'll be acting as an additional teaching assistant for this particular course, which is the finite element method and computational structural dynamics. The course is currently being tutored by Professor Manishi Khande, who is professor in Department of Earthquake Engineering, IIT Roorkee. So those who are coming to this session for the first time, just brief information. So these sessions are particularly meant to interact with our learners. We'll be discussing some of the important concepts which are required to solve your assignment questions related to this particular course. We'll also be solving some of the sample questions which will be helpful in solving your questions related to the assignments. We'll be solving some of the doubts which will be coming from your end, and other than the technical part, if you have any other query which you think we can help you, and if it's possible from our end, definitely we are here for you. And we are also recording this particular video, so at the end of the session I'll be uploading this video to my YouTube channel. If you have any query related to any part of the course, you can post your query in the comment box, and definitely we'll try to address your query. So let's start with our sample questions today. So today's question is basically based on the formulation of the stiffness matrix and solving it using the linear simultaneous equation. Will utilize the linear simultaneous equation to solve the stiffness matrix. And in the similar line, we are having the first question for you. So here is your first question. So as shown here, the beam has been discretized in two beam elements with degree of freedoms given by red arrows. You need to formulate the global stiffness matrix, the mass matrix, the global load vector, and then with the corresponding appropriate boundary conditions, you need to solve the eigenvalue problem to obtain the eigenvalue and the eigenvectors. Then you need to ignore the inertia effect to solve the system of equations using Cholesky factorization. These are your material properties. Your elastic modulus is 200 gigapascal, Poisson ratio is 0.3. The density of the material is 7850 kilogram per meter cube. The cross section of the beam is having the width of 50 mm, depth of 100 mm. The applied force is 100 kilonewton, which is acting at the middle of the beam. So, and you are, yeah, and this particular beam arrangement, if you see, it's a simply supported beam along with an internal hinge at the uh, at its center, which is located at equivalent distance from both the ends. You need to provide this particular six values. So first you need to calculate what is the two eigenvalues, first two eigenvalues. Then you need to normalize the eigenvector. You need to make the global force vector at elements 3, 2 and 4, 3 of the lower triangular matrix L of the Cholesky factorization. Then along with that you need to find the intermediate solution vector x such that Lx vector is equal to f, and you need to find the ultimately what is your solution vector x. So this is the question. Let me distribute this thing in two slides if possible. Screen. I'll paste the content again. Yeah, so first you can work on this. You need to find the first two eigenvalues. So before working on these particular values, first you need to formulate the global stiffness matrix and the mass matrix and the global load vector of this particular beam. So first you do that, and then we can work upon how we can solve the eigenvalues and eigenvectors for this particular problem. So just read this question, try at your end, and then we'll see what we can do. The most minimum thing you can do, try to make the stiffness matrix. So a stiffness matrix is like, first we'll make the stiffness matrix of this particular beam element, then we'll make the stiffness matrix of this particular beam element, and then we'll combine both the stiffness matrix to make a global stiffness matrix, which you can utilize in solving the in getting the solution of this problem. So let's see. to the solution. So as shown here, the beam which is given to you, it's having a simply supported beam with internal hinge in between. So the configuration of beam which we can see, it's having one pin support at left end, one roller support at right end, then you are applying a point load to the middle of the beam. The first part of the beam is this, the second element of the beam is this. From here to this distance is your L by 2, this distance is your L by 2, the whole length is L, and then you are having a distributed loop at the right hand side of the beam. Now corresponding to that, first we need to formulate the stiffness matrix. So we'll formulate the stiffness matrix for element 1. So this part of the beam will formulate the stiffness matrix. Let's see how to do that. So this type of thing you would have done in your structure analysis part, where you know how to formulate the stiffness matrix. Another way also we have learned into our initial tutorials, so you can utilize the shape functions also to formulate the stiffness matrix. That is B transpose your B transpose EI, and then this is B matrix multiply with it. So this particular aspect will give you what is the stiffness matrix look like. So this is your stiffness matrix. This B matrices generally consist of your shape functions matrix. You can utilize them. Uh, we know what is the shape functions for let's say one element, uh, two element, two noded one element. So the shape functions for them is given as n is equals to n1 of x, n2 of x, n3 of x, then this is your n4 of x, where your x is starting from your left hand, right? So this is your shape function matrix. So if you see what is the n1 and n2, so your n1 of x is given by 1 minus 3x square by L square plus 2x cubed by L cube. Your n2 of x is x minus 2x square by L plus x cubed by L square. Then your n3 of x is given by 3x square by L square minus 2x cube by L cube, and then your n4 of x is given by minus x square by L plus x cube by L square. So utilizing this shape functions, you can formulate your B matrix. The B matrix, for your two noded element having a 2 degree of freedom each, is given by n1 0 0 and 2. Then your sorry, this is again n1, then n2 0 0 and 2, and 3 0 0 and 3, and 4 0 0 and 4. So this is your B matrix, which you can utilize uh, for obtaining the shape is your stiffness matrix. And you can put the all the shape functions here. These shape functions, like I'm not going to derive it. We have already seen in our initial tutorials, and I guess you can refer the previous lecture notes also for that. You'll come to know how to derive the shape function for two noded element having the 2 degree of freedom. Then there is another method. So let's say if you don't remember this particular relation for the stiffness matrix, then you can go with your conventional solid mechanics theory. So I'll be using that. I'll show you that also, second method for obtaining the stiffness matrix. So what is your second method? So let's assume this is your B, having the material and geometry property of EI. Let's say at one end you are having certain amount of rotation, and then displacement, then this end, and this is your another rotation at another end, and another displacement at the second end. Okay, so let's assume some approximate function. Which is given by v of x. So since it's having the 4 unknowns, you will be taking the third degree polynomial, which will be having the 4 terms. So it's a0 plus a1x plus a2x square plus a3x2, right? And then from our problem, like let's say this is at this end we are having the generated moment m1 with rotation theta 1, then another this is m2, this is theta 2, then here you are having force 1 and your displacement 1 f2y, and then your displacement v2, right? Once you are having this, you can assume the approximate function, and then one by one we'll use the boundary conditions and obtain what are the coefficients of this relation. Let me show you. you know your displacement at the left hand side is 0, so mu 0 is 0. So correspondingly with the help of this you will get a naught as 0. Then you are having d mu by dx, no, at the 0. It's like for the fixed and conditions this is also 0. No, this will be having some rotation theta. Yes. For our problem, since it's having the pin support at the left side, so it will be having some rotation, and that will give you your a1 as theta 1, right? Then similarly for mu of L is 0, so that will be a1 L plus a2 L square plus a3 L cube as 0, right? Then your second derivative, which is the rotation at the right hand end, is 0, is not 0, it's theta 2, so that will give you what's the a1, so it will be a1 plus 2 a2L plus 3 a3L square as theta 2. Okay, so this is your first equation, this is your second equation, this is your third equation, this is your fourth equation. So with the help of this, so you already know what is your a naught and a1. So with the help of this you can find what is your a2 and a3 with these two equations. So by solving this, the relations which you will get for a1 and a2 are 2 by L cube mu1 minus mu2 plus 1 by L square, your theta 1 plus theta 2. Similarly for the a2 you will be having minus 3 by L square mu1 minus mu2 minus 1 by L, your theta 1 plus theta 2. Okay, so your corresponding approximate relation will be given by so this is what your approximate functions look like. So this is the approximate functions corresponding to your, let's say, displacement. So before moving further, like I want to show you the sign conventions which can be utilized. So from beam theory, we know that you are having M1 here, M2 here, then you are having certain displacement, let's say F1y, then you are having F2y. So from the beam theory conventions as we used to perform for making the shear force diagram or the bending moment diagram, so here we assume that your hogging moments are positive, as well as in your shear force case, the clockwise is your positive case. And in the similar line, you are having the applied moment M1 and M2. So what are the conventions which we use to make while making the stiffness matrix? So this is your positive, and here you are having F1y, and here you are having the F2y. So this is your stiffness method, and this is your beam theory. So these are the positive conventions. So whatever rotations, so let's say it has been generated at the beam level, if we want to utilize them and want to use those responses to make the stiffness matrix, so accordingly we have to convert the sign conventions used in the beam theory to a stiffness method. So we know from beam theory your moment at any place x is given by d2e by dx by dx square into ei, then your displacement, your shear force x is the third cubic into ei. One second. So you are having your moment is given by like this, your shear force is given like this, and then to utilize them, so we know our approximate solution for the displacement is given by this particular function, and then to use this function you f and y is equals to your shear force 0 is given by ei d of 0 by dxt. So this will give you the shear force at 0 location, is at the initial part at the origin of the beam, So it's given by EI by L2 12 mu1 plus 6 L theta 1 minus, sorry, this was your E2 and E3. Similarly, your moment is given by m1 is equals to minus m of 0 minus ei df square. So it looks like ei by l cube. So it's 6l mu1 plus 4l square theta 1 minus 6l mu2 theta 2 plus 2l square theta 2. So that was your shear force and this was your moment. Similarly, you can get your F2y and then your M2. So we are following this convention. So here if you see F1y in the same direction, so we have kept the same signs for them. Then here you are having the M1. So your M1 looks like this, but in your stiffness matrix which we are going to formulate, the M1 is considered in this particular direction, so definitely we need to take the negative of the second derivative of the displacement. Then your F2y looks like this, and then your moment look like this. Minus E of L is equals to minus EI this is given by EI by L cube minus 12 mu1 minus 6L theta 1 plus 12 mu2 minus 6L theta 2. Your M2, which is your in positive direction in the similar direction, so it is given by EI your d2v L by dx square. So it is given by EI of L cube. So 6L v1 your displacement plus 2L square theta 1 minus 6L into plus 4L square theta. So basically you need to take the second and the third derivative of this relation. So once you have these force functions available with you, and these are your particular unknowns which you need to find, this is your material and the geometry properties, then you can utilize these particular relations to formulate your stiffness matrix. So by using this relation you can get the stiffness matrix, which is given by our F1y, M1, F2y, into EI by L3, which is given by 12, 6 of L minus 12, 6L, 6L, 4L square minus 6L, 2L square minus 12 minus 6L, 12 minus 6L, 6L, 2L square minus 6L, 4L square. U1 theta 1, then this is your minus second displacement and minus second rotation. So this is how your stiffness matrix look like for two node beam element with each node having two degrees of freedom, right? So this is your particular stiffness matrix. So there's one way which you can use the shape functions and form your stiffness matrix. There is another way which you can utilize by using the conventional beam theory. You can use that particular beam theory and then you can formulate your approximate function. Using that approximate function you can, and utilizing the beam theory, you can generate your forces as well as the shear force at both ends. Then corresponding to that you can formulate your stiffness matrix. So that was about your stiffness matrix. Now in the similar line we will formulate your mass matrix. So your formulation of mass matrix is given similar as your stiffness matrix. So we'll be using the shape functions to form the mass matrix. So your mass matrix is basically given by rho times your transpose of shape function matrix, then shape function matrix, then here you will be taking the dv. This dv you can write it as the a times dx. So your mass matrix then will be given by rho of a and times a then dx. So this is how you can get your mass matrix. So once you have mass matrix, so just try once. You know what your shape functions look like, and these are the particular relations with which you can formulate your mass matrix. Try to obtain the mass matrix. Just obtain the first few elements. I'm having the final relation with me. Let's see whether we are on the same page. So this is how your mass matrix basically looks like. So I'm having a final relation with me. It's your rho A L by 420, and this is given by 156, 22 L, 64 L is basically your length of element. So L is basically your L by 2. So yeah, using this, your stiffness matrix basically looks like yeah. Yeah, so let's form the stiffness matrix for our case. So the same thing, your stiffness matrix for both the elements. Looks like this, which is K1 is equals to K2. After putting the value, and 833 0.4 divided by 12.6 minus 12.6 minus 6 4 minus 6 2 minus 12 minus 6 12 minus 6, then you are in 6 2 minus 6 4. So this is your stiffness matrix for both the elements. So with the help of this, in general, your mass matrix look like this. So 156, 22 L, 54 minus 13 L, 22 length of element, 4 length of element squared, minus 6 times length of element, 2 times length of element squared, sorry, length of element, minus 3 times of length of element squared, 54, 14 times length of element, 156 minus 20 times length of element, minus 13 times length of element, minus 3 times length of element square, minus 22 times length of element, then by 4 times length of element. So for our case, considering the both the elements, your mass matrix looks like this. So it's 0.0934 5 2 3 8, and here we will be having the same coefficients: 156, 22, 54, minus 13, 22, 4, 13, minus 3, 54, 13, 156, minus 22, minus 13, minus 3, minus 22, then we'll be having the 2. So the corresponding, so this is your stiffness matrix at local level, and this is your mass matrix at local level. Then your displacement vector is given by, so for the first element, if you see your displacement vector, so at this particular end your displacement is, sorry, your force vector. So at this particular end you don't have any forces acting, neither the force neither the moment, but here you are having a particular force which is acting at this end. So from the, so we will be considering the fixed end moments. So those fixed end moments will be 0, 0, minus 100, 0, transpose. In the similar direction, the fixed end moment for the second part, when your beam is subjected to the UDL load, is given by WLE by 2, 1 length of element by 6, 1 minus length of element by 6. Taking the transpose of this, what we'll get is minus 50, minus 50 by 6, minus 50, 50 by 6, and the corresponding transpose. So this is how your force vectors look like. For the left hand side of the beam, you are having only a single point load which is acting at another node. Then here at the second part of the beam you are having the UDL, so your fixed end moment something look like this. So after the formulation of the local matrices for both the ends, now our point of interest is the formation of your global matrices. So let's say first for the stiffness matrix. So for the global matrices, since your stiffness matrices are same, so we need to, like, all the particular elements of the local matrices will remain same. Only we need to connect the elements of the matrix at the joint of both the elements. So it will be something like this. So your K global will be like this. So it's your K1, K11, then we'll be having K12, then you are having K13, K14, then here you'll be having the 0, 0. Again here we'll be having the K21, K22, K23, K24, and here we'll be having the 0, 0. Here we'll be having the K31, K32. Then here at this point you'll be having the K33 of the first matrix, and then you'll be having the K1, right? And in the similar direction you'll be having K34 plus K12, then K13 and K1. Here we'll be having K41, K42, K43, K41, K42, then here you are having K43, then K4. So this is how your global stiffness matrix look like. So you are having the both the stiffness matrix, both of them are same. So we'll only club the elements which are common between both the matrices. So in the similar line you will be having a mass matrix. So here we have M11, M12, M13, M14, 0, 0, then M21, M22, M23, M24, 0, 0, then here again M31, M32, M33 plus M11, M34 plus M12, then M13, then M14. Similarly M41, M42, M43 plus M21, M44 plus M22, M23, then here we have the M24. Then this particular thing is 0. Then this is your M31, M41, M32, M33, M34, then M42, M43, and then M4. So this is how your mass matrix look like. The final answer which I am having with me after the formulation. So I think I have written the code in the octave so that I can show you. Yeah, I'm having the code. So let me share the screen. So first of all, let's see that. So this is your stiffness matrix K global. This is your mass matrix M global. So utilizing them K global and M global. Uh, so this was your initial part of the problem as mentioned here. So you need to apply the appropriate boundary conditions and you need to solve the eigenvalue problem to obtain the eigenvalues and eigenvectors. So first of all, we need to formulate the global stiffness matrix and the mass matrix. So let me show you. So at the formulation level, I have shown you how we are getting the global stiffness matrix and the global mass matrix. Once you have that, let's do the calculations in the octave. So this is the octave. It's a octave G. It's having a GUI interface. So these are the mathematical solver tools. So in the similar line as we have seen the maxima in the last class, so we can perform some, let's say, matrices operations or another algebraic problems, the linear simultaneous problem in this by using the this tool. Octave is highly recommended like for this course or let's say for any of your numerical calculations since it is an open source software, so you can use it for any of your calculations, so it is easily accessible to everyone. So I have written the code to solve this particular part. So here, let me share the screen. So yeah, this is the octave. It's having a GUI interface which is shown here. So it is as mentioned, you can use as an alternate to MATLAB. So this tool is basically used for performing the numerical calculations. It's having some inbuilt functions and modules which you can utilize them to perform various complex calculation associated with your numerical problems. So in today's problem, like we'll try to solve it using the octave. Just look at the interface once and then I'll show you. So here you can see like this is the initial interface, so it will basically help you to navigate your files which are available in your system. Then this is the workspace, so basically whatever variables or the identifiers which you are using, and these are the literal values to those identifiers. So this thing you can utilize them, and then here you are having your command string. So whatever calculations you are performing, this has been recorded here, and you can utilize this command string to navigate through your code which you have performed. Then at the right hand side, this is the text editor. So if you have worked in another other programming languages, you know what is a text editor. So this text editor works in the similar direction as your Word, or let's say another text editors work. So whatever calculations you want to perform, you can give the commands for them at the right hand side, and here is the parameters associated with them. So here you can write all your commands along with your comments, or let's say whatever documentation you want to do. And this the like the good part about this code is you can formulate it line by line. So let me put file new script. Yeah, so with the help of this you can add it new. Then here is the documentation. So if you don't know, so it will basically the guide manual which you can use, like how to work with the Octave. This is the workspace for that. Then this is your command window. So whatever text you have written here, once you have executed here, the compiler, let's say the interpreter, will formulate that particular text in the command window, and you can utilize those particular code, whatever execution which have been done at the compilation end. You can see that particular execution of the code by operating in this command window. So let me show you. So first, these are your variables. So I have written it here. So yeah, let me clear the command window. So these are my initial calculation which I have done. You can just type clc, and this will clear your screen. And once you will type the clear all, it will basically clear the whole memory which has been allocated till now while you were executing. So let me show you. So these are the initial inputs. Let's say cross-section properties, then you can define the elements length also. I'm just copying this, I'll paste it here. So you can select this particular piece of code, and then you can execute here. So this is the part, either you can select the F9 or you can select on the run selection. Once you have selected the run selection, you can operate in the command window. So you can see your whole code is executed. So if any of the value you want to check whether it has been stored in the memory or not, you can just write the Young's modulus, and to run the command you can click on the shift enter, and yeah, it has been stored in the memory. Similar, let's check for one more variable which is Ali. So this way. So you can see that in the editor we have written the particular script. So as shown here, these are your initial input p, new, row, p, w, l, whatever inputs are there we have written in the command window, in the text editor. Once you have written this, then our next task is to formulate the matrices. So you know how your stiffness matrix look like. We have solved it here. So these are your stiffness matrix at the local level. So EI by L cube, 2L 6 minus 12L, and these are your that's a displacement factor. This is your force factor, and this is your stiffness matrix. So this is stiffness matrix. You can copy it here. You can paste it here, and this is your stiffness matrix. So again, you can select this particular piece of code. You can run selection, and it will get executed at this. So element stiffness matrix. So this is your command window. You can see it has run here, and let's check here what are the values of your stiffness matrix at the local level. So this is your stiffness matrix at the local level. In the similar direction, we have written the. If you guys have any doubt in between, if you want to know how we are executing any piece of code, please stop me right away, or you guys can even post it in the comment box. And if you want me to take a special session, let's say on the Octave or Maxima or the MATLAB or let's say Python, in any of the language you want me to perform, please let me know. Then this is the formation of stiffness matrix, and let's check for the mass matrix. So this is your particular mass matrix. This is your editor. I've already written the code here. You can copy paste it. You can select this particular piece of code, and then you can run selection. Again, you can see the command has been executed at the compilation end, and this is your mass matrix. Stiffness matrix, mass matrix. Once you have this, then you need to formulate the global. So this particular piece of combination of both the matrices, as we have written it here, you can use that particular product. So you can see your 3, 4 and element has been added with the 1, 2 element in both the stiffness and the mass matrix. So this is how your global and the stiffness matrix will work. And let me select both of them. And then you can execute here. And then you can run the selection, and if you see in the command window, so you can check how your global matrix looks like, and how your global mass matrix looks like. Yeah. So these are your global stiffness matrix and the mass matrix. Let me check whether I'm correct or not. Yeah, so these are the final stiffness and the mass matrix. So instead of doing the calculations, let's say at the calculator level or by manually, you can utilize this numerical tool and simplify your let's say whatever solution you are making. So once you have that, so you are having your global matrix with you, you are having your mass matrix available with you. Once you have both of them, and let's check what is has been asked in the next part of the question. Yeah. So once you have them global and the mass matrix, you need to apply the appropriate boundary conditions and you need to solve the eigenvalue problem. So you need to apply the appropriate boundary conditions. You need to solve the eigenvalue problems to obtain the eigenvalues as well as the eigenvectors. So let's apply the appropriate boundary conditions. So if we see in our particular problem, so your displacement here as well as here is 0, right? So at both the ends you are having the displacement as 0. So in your particular stiffness matrix, if we say your this particular row, let's say this particular column corresponding to your first element, since it will get multiplied with 0. In the similar direction, your fifth row as well as your fifth column, sorry it's not straight, so you can basically reduce this matrix, since as you can see this particular rows and columns will anyhow will get cancelled because the corresponding responses associated with them are implicitly 0. So in that case you can remove that. Similar in the mass matrix, so you can remove this particular column and this particular row, then you can remove this particular column and this particular. So then you'll be having the k reduce and the m reduce. So once you are having the k reduce and the m reduce, you can obtain what are the eigenvalues and eigenvectors by taking inbuilt function. So the inbuilt command for eigenvalues and eigenvectors, so let's say these are your eigenvalue, so these are your eigenvectors, these are your eigenvalues, so the corresponding phi is your eigenvector, this is your eigenvalue. Once you have this, you can utilize the EIG function to get the corresponding eigenvalue as well as eigenvector. So this particular command will give you a matrices which will be corresponding to the eigenvectors, and this will give you a diagonal matrix. Each diagonal element will correspond to your eigenvalue. So let's do it here. So let me write the code in the text editor. So your k global, so your k reduce will be, let's form the matrix. So anyhow your first element is not there, so you'll be having k global of second element. So k global, the global 2 2, and we're getting 2 3, and we're getting 2 comma 4, and now your fifth row is not available, so it will be your k global, which is 2 comma 6. Then we need to change the rules. 3 comma 2, 3 comma 3, 3 comma 4, and here we get 3 comma 6. Four comma 2, then 4 comma 3, then here 4 comma 4, 4 comma 6, then if it throws empty, we will be using the sixth row. 6 comma 4, and then we have 6 comma 6. So this is your reduced matrix after removing your vectors corresponding to your null responses. So let me execute this on selection. Let me check the command window. This is your k reduce. Let me check the values. So the answer is there with me. It's equal to 0. So this we are correct. So similarly we need to form the reduced matrix for m. So in the m reduce you just need to replace k with n. So there is one way, like rather than typing the whole kk again, we can just open the new script. We can paste your whole command here. Instead of k, let's say edit, and then replace. You can find the key and replace the whole script with so this is your next, and then you can replace all. So this is your new matrix m reduce. Then you can paste it to our part. So once you have this, then you can execute this part. Your and reduce factor, then you can run selection, and this is your and reduce. So let's check into a command window. So this is how your and reduce look like. So let me check with the value which I am having, 0.0934 5238 into 4. Yeah, so we are almost in similar right direction. So once you are having your k reduce matrix, you are having m reduce matrix. So your k matrix is available with you, your mass matrix is available with you. So now it has been asked to calculate the eigenvalues and the eigenvectors. So as shown here, you need to apply the appropriate boundary conditions to obtain eigenvalues and eigenvectors. You need to basically ignore the inertia effects and solve the system of equations using cholesky factorization. So once you are having the eigenvalues and the eigenvectors with us, the only part is to no. So we are having the stiffness matrix and mass matrix. So you know your equation of motion look like mu double dot plus cu dot plus k is your forcing function minus dt. So here you know you are basically neglecting the inertial effects, so this term will become 0. Anyhow we are not considering the dampening in the system, so this will be 0. So only thing you will be having is the kx into f. So this is how you can utilize to calculate your let's say you need to get the solution using the cholesky decomposition. So before that, let's evaluate what your eigenvalues and eigenvectors look like. So this is your particular command to get the eigenvalues and the eigenvectors. So for getting this, you are having 5 comma lambda. Your eigenvalue is k reduce comma m reduce. This is your command window. Sorry, I pasted it here. Okay, anyhow you can do it here also. No issue. Yes, there's some issue with the command. Let me check this. I k reduce and reduce 5 comma lambda. Okay, the brackets are this bracket. So the parentheses are the round curve brackets. Now let me execute it once again. And you can run selection. Let's look what is there. So yeah, these are your corresponding eigenvectors, and these are your eigenvalues of the system. Yeah, so we are almost correct. So yeah, these are your corresponding eigenvectors for each response, and these are your corresponding eigenvalues. So once you are having eigenvectors and eigenvalues available with you, so let me copy paste here this making so yeah, what has been, so these are your eigenvalues and matrices corresponding to your eigenvectors, and these are your eigenvalues. So here it has been asked first to calculate two eigenvalues, and then after arranging the eigenvalues in ascending order. So your first two eigenvalues are this one. These are your first two eigenvalues. Then you need to calculate your first mass normalized eigenvector. Then this is your first mass normalized eigenvector. So this is your answer. Yes. So these are the answers for your first and second part. Then you need to obtain the global force vector F after applying the boundary condition. So just evaluate what is the global force vector F. So you are having your stiffness matrix with you. You don't need the stiffness matrix. So global force vector, I guess we have, okay, we haven't evaluated it yet. It's basically you need to utilize the appropriate boundary conditions, and you can need to calculate what are the forces available at both ends. This you can try from your end. force vector for the given problem. If you see, this is a problem where here you are having the pin support, here you are having the pin support, here you are having basically the roller support, then here you're basically applying a force P of 100 kN. Then here you're basically applying a UDL. So corresponding to that, your force vector will look like. So here you won't have any force, so at this particular node you don't have any force. Then here you are having the 100. This is your 100 kilometer. This is basically your 100 kilometer per meter. Yeah, this is your 100 kilometer per meter. So at this particular end you will be having the 150 from here. Then from here, you know, it's minus WL square by 6. So the corresponding value is the minus WL square by 12. So yeah, but for this it's L is 1. So yeah, it's given by WL square by 12. So we'll be having minus 50 by 6, here minus 50, and here 50 by 6. So the whole transpose. So this is how your force vector looks like. Now as we already know, we'll be having corresponding responses as 0. So your final force vector which we require from our end is 0, 50, minus 50 by 6. So both this element and this element will get negative, and this is the 50 by 6. So this is your part 3 for answer. Then you need to perform the Cholesky factorization. Let's see that how to do this. So why we want Cholesky factorization? Because ultimately whatever matrices we are having with us, the stiffness matrix which we are having with us, K global, which we want to reduce into, like we want to decompose those particular stiffness matrix into your lower triangular and the upper triangular matrix, and those lower triangular matrices which we can utilize them to perform we can utilize them to perform the forward and the backward substitution to get the corresponding solution of the system. Just a minute guys, I'll come. Hold on. then for the cholesky factorization, ultimately whatever K matrix we are having, we want to decompose into upper triangle and lower triangle. So this is your stiffness matrix. You want to decompose into lower triangle and upper triangle. So for that there is pseudo code. So for obtaining the first element, so your first element, if you see that your pseudo code, so your whole first column, let's say L comma 1, you can get it like this. So let me directly do into the octave. So we have obtained the K reduce and M reduce matrix. Then performing the cholesky decomposition. So you already know the pseudocode for cholesky decomposition. Let me write it here again. So it's basically your L matrix comma 1 K of comma 1 of square root of K 1 comma 1 so function f9 function f9 and just right click and then I'll run selection. Then your next set of element, which is your second diagonal element of your L matrix, is given by a square root of K 2 comma 2 minus L of 2 comma 2 1 dash to the power 2 and this is your L2. Then this is your L raised to 4 comma 2 will be having K raised to 4 comma 2 minus L of 3 raised to 4 comma 1 then you want to perform the operations for the whole matrix. L 2 is to 3 comma 1 divide by L 2 comma 2. Then for you having L3 comma 3 square root K3 comma 3 minus L 3 comma 1 h to the power 2 minus L 3 comma 2 h to the power 2, then this is your part. Then is L 4 comma 3 then you are having K 4 comma 3 minus L 4 comma 1 into L 3 comma 1 minus L 4 comma 2 into L 3 comma 2 divided by L 3 comma 3. So this is your particular element formulation. Let's run this. Let's see whether there is any error or not. Command window. K is not defined, so yeah, we need to operate not with the K, we need to operate with the K reduce. So let's control X, let's perform the same thing. K K underscore reduce. Replace all and then run the code. Control C and then let's paste it here, cholesky decomposition, and then let's run the code. So we are having the issue. Let's check there we are making a mistake. So it's L1, L22, L3 is to 4 comma 2. L32, L43. Then we are having one more element, which is L4 comma 4 equals to square root K 4 comma 4 minus sum L 4 comma 1 is to 3 and then the sum. Run selection, arrow solution, let me clear out, and then let's see event command run selection. So let's do the cholesky decomposition. Like you can do it manually also. So let's operate cholesky decomposition from the env function, and I will see the code in the next class, like how to do the pseudocode there with us. can check in the guidelines also. So let's see documentation. Matrix manipulation. Let's search from here. Let's do it with the initial editor. I dash with show function of k underscore reduce. Then let's run selection. Guys, we'll check with the cholesky decomposition. I'll just give you the thing which is basically happening. So once you will get the cholesky decomposition, you will be decomposing this into upper triangular and the lower triangular matrix. And once you are having the upper triangle and the lower triangular matrix, you will be performing the forward substitution. So we know Alex equals to F. So your first part of the element is given by f1 by L comma 1 comma 1, then x2 by f of 2 minus L of 2 comma 1 multiply with x1 divided by L2 comma 2, then your x3 is given by f of 3 minus L of 3 comma 1 into x1 minus L of 3 comma 2 into x2 divided by L3 comma 3, then we'll be having x4 which is given by f of 4 minus L of 4 comma 1 into x1 minus L of 4 comma 2 into x2 minus L of 4 comma 3 into x3 divided by L4 comma 4. So your x bar, which is intermediate vector which you need to show, x1, x2, x3 and x4. So the final value of x bar which is there with me is your 0 0.0 minus 0.042426, 0.00938819 and 0.058697. So this is your x bar. Similarly, for the backward substitution, we're getting the final solution. You are having utilize the L transpose into x bar, and similarly you will be calculating all the equations which are forming using this particular matrix, And once you have this, your final solution as solved here is given by minus 0.000 whose term side over 0 minus 0.00325 double 0, and here you are minus 0.84 times 0 25 triple 0, and here you will be having 0.00052 So this is how your forward and backward substitution is. I am facing little issue with the cholesky factorization. The code which you have executed, it's not working. Let me check and we'll get back to you in the next part. But this is how you will obtain the solution. So first, let's see from the start. You have formulated the global stiffness and mass matrices. Then after that, once you have done this, you have applied the boundary conditions and remove all the negligible vectors which are corresponding to the null responses. And once you have done that, you will need to perform the eigenvalues and the eigenvectors, find the eigenvalues and eigenvectors for your reduced matrices, and after that you need to perform the Cholesky factorization on that reduced matrices, and it will basically give you the lower triangular and the upper triangular matrix. Those lower triangular and the upper triangular matrix you can utilize it to perform the backward substitution and the forward substitution, and you can find it what is your final. So that was the part for today. uh, I think we have learned how to use the octave. There is a little issue with the pseudocode which I have written for the, let's say, for the Cholesky decomposition. I'll check that and we'll discuss this thing in the next class. Meanwhile, like Cholesky decomposition, pseudocode or the algorithm is already discussed in the lectures. You can utilize them. You can use the octave function to find it out how to work with the matrices, or let's say how to perform this numerical calculation. So this was the initial idea I want to give. If anything else is there, you can post your comment in the YouTube video, or you can also come to the next class. We'll discuss it there. Thank you so much for your time, and let's meet at 6 p.m. next next work.